Hello everybody to our latest edition of the KGS virtual seminar. I'm delighted to have with us today Stephanie Pilkington. Stephanie, Dr. Pilkington, we'll keep it formal, which is important, is an assistant professor in civil engineering technology and construction management. And she's gotten her PhD and her MS from Colorado State University and her BS from Virginia Tech. Her core research interests relate to meteorological natural hazards and how they affect communities. Her expertise is in community resilience to natural hazards and modeling hazard impact and recovery on a systems level. She also leads the PhD disaster research group, where they focus on transdisciplinary research that incorporates aspects of civil engineering, computer science, atmospheric and earth science, social science, economics, and policy and management. And I think Dr. Pilkington is also a storm chaser, which sounds, have you ever gotten your car rolled over by a tornado?
No, if you know what you're doing, you don't actually get that close.
Well, great. Without further ado, I look forward to her presentation on a new ranking system for hurricanes. Take it away, Stephanie.
All right. I'm going to go ahead and share my screen here, guys. All right. We all good? Everyone can see that?
Looks good.
Perfect. All right. So, hello, everyone. Like Dr. Shoemaker said, I am Stephanie Pilkington. I am an assistant professor here at UNC Charlotte in civil engineering technology and construction management. And today I'm going to talk a little bit about this hurricane system, a ranking system we came up with in the model in order to actually rank said hurricanes. And we started this back in like 2015 and been modifying it ever since and updating it with each hurricane system, with each hurricane season. So we're going to kind of go through a bit of what it took to go and create this model, and then a little bit on the neural networks that run the model, and perhaps a little bit more on how it's performed over the time. So, oh, come on, if it lets me. Okay, that works. So like I said, my name is Stephanie Pilkington. I have storm chased. So this is the first tornado I caught actually up here. This was back in 2010. This was in South Dakota, and I think it ended up being an EF4. Luckily, it didn't really hit any structures or anything. It was pretty much just open farmland that it went through. So I do storm chase. I do also do field reconnaissance, which involves going and looking at the structures post-event to try and assess how they were damaged. So this picture down here is from the Nashville tornadoes in 2020. I literally flew out right before everything shut down. Came back and was then basically in lockdown. So that was right then. And then I've also got a robotic dog that I'm trying to gear up to use to go into said structures and get a better look at some of the failures within those buildings due to meteorological hazards.
Is that like a Boston Dynamics dog?
It's similar. So I actually got it from Ghost Robotics, is the name of the company. There are two makers of this type of robot that I know of, and one is Boston Dynamics and one is Ghost Robotics. But yeah, it's very similar to that.
That's amazing.
Yeah, it's so cool. Once I get it set up, maybe I'll do a presentation on that thing, but just walk it by. Anyways, so before we get started, I wasn't sure. I know geography covers quite a spectrum of different areas, and I wasn't really sure what everyone's background was. So I wanted to go through a little bit of what do we need to know about the hazard before we model it? What do we need to know about how we're going to model that hazard itself? So we're going to go through a little bit about hurricanes. And so if some of you have a meteorological background, this is going to be incredibly redundant. So I apologize in advance, but it's more so to get everyone on the same page. And then we'll talk a bit about machine learning and how you have to get your data just right to do it in machine learning. All right, so let's start off with modeling hurricanes. So we currently model hurricanes. We talk about forecasting. And forecasting is where we go into forecasting their landfall, their intensity, all these types of things. Whereas we also have the physical impact. So what happens once that hurricane makes landfall? So the forecasting part is looking at the science behind the meteorology of hurricane formation. We're looking at basically a synoptic or mesoscale. That depends on who you ask. And then because it's right at that borderline, it has more lead time than, say, forecasting severe weather because it's on a larger scale. Typically what happens is there's an ensemble of models that will run, and the ensemble creates those graphics you see from the National Hurricane Center, where you have that kind of forecast cone. And that cone represents an error, so that landfall can be anywhere within that cone. We also tend to categorize our hurricanes by the Saffir-Simpson scale. So the Saffir-Simpson scale is only indicative of the wind speed. In the past, we have tried to put in storm surge, but it was found that there wasn't a direct linear correlation between the two. So it was pretty hard to keep that consistent, because sometimes you would have a storm categorized as like a category 2 by wind, but say a category 3 by storm surge. And so that kind of got taken out, and now it's purely just wind speed. Storm surge, in fact, is usually the last one to be forecasted. So if you're watching a hurricane as it tracks towards land, storm surge is typically the last one, because it's a more complicated modeling process, specifically for where it makes landfall. And we'll talk a little bit about that going into it. So what we care about as people is really just, how does this impact us? And that's the physical impact part of this. So you have damage to your structures. You have overburdened stormwater systems that are just going to overflow because they can't handle the volume of water. Power outages, especially since mostly on the East Coast, we don't bury our lines. Living in Colorado, it was great. We bury all our lines. Everything's fantastic. Barely have outages. Then you also have things like road washouts and closures, because they're also subjected to these same type of forces. But you'll notice that each one of these comes from a different hazard from the hurricane. Damaged structures can be from wind and flooding. Power outages are most likely going to be from wind. Road washouts are going to be from flooding. So these are your different types of hazards are impacting different aspects of your infrastructure and causing a different impact to your community. And unfortunately with hurricanes, these are multi-hazard events, so you're just going to get all of them at once. All right, so before we can even go into modeling the physical impact of a hurricane, so if we wanted to say we want to model hurricanes now in terms of impact instead of intensity, what does it take to translate from forecasting on a meteorological level to forecasting in terms of impact? And first things first, we have to understand the hazard we're working with. We can't just, from the engineering side, assume we'll just go with the engineering part without considering the meteorological part, because that is important to the problem. And I laugh as I say that because that's a common thing you'll see. But so to start off, and again, this might be incredibly redundant for people who are more familiar. A hurricane is essentially a low pressure system. The center of it, it's got a very low pressure. On the right side, relative to its motion, it also has stronger winds. So that's, if it's moving, say, into the page for this diagram, the right side is going to have stronger winds relative to its motion. As such, what will correspond with that is higher storm surge. So this is why when they talk about New Orleans and Louisiana and Katrina, the relative position of Katrina to New Orleans played a role in the devastation with that. And it could have actually been much worse, because New Orleans actually fell on the left side of Katrina, where there was less storm surge. So if you can believe it, that 28-foot storm surge and what flooded New Orleans was actually the weaker side of the hurricane. relatively speaking. And so you have to kind of keep that in mind with, once you start bringing these hazards on land, if I have something in this right-hand side of my hurricane, that's going to react differently than on the left-hand side. So where those hazards occur relative to land when it makes landfall become highly important. All right, another thing we want to understand is how exactly do those hazards affect our infrastructure? So the things that we care about being damaged. So to start off, let's talk a little bit about buildings. So buildings with wind create interesting systems. And let's say you have a fully enclosed building, which is this first diagram. You have wind blowing on it and you create this forward pressure on the windward wall, is what we call it. But then on the roof, you actually create what we call an uplift force. So as the wind moves up over the roof, it actually creates a kind of suction on top of the roof. Same thing with the leeward side, so the back side that's not directly exposed to the wind. It's going to have a pull to it. So what ends up happening is you get exerted forces in these directions. Structurally speaking, a lot of what we do in design, we design for gravity loads, and gravity is going in the other direction. Now, gravity can help counteract these uplift forces, but if they're too strong, it'll overcome gravity and will try and push up on your roofing system or pull up on your roofing system. And if we don't design for that, we don't design our connections between, say, the roof and the wall with the consideration, the fact that our force is going in the opposite direction in extreme circumstances, then you get failure. So the other part of this is what happens when you have this enclosed building and all of a sudden you say you punctured it with debris and now you've opened part of the building. So this is where you can disprove anyone who tells you that you should open your windows during a tornado. You shouldn't do that. Because what ends up happening is when I open this part of my structure and the wind direction is still going the same way and open it on the windward side, I'm now creating another pressure force on the inside pushing out on my wall while still having this exterior force pulling out. Same thing happens with your roof, and this is actually common as to what leads to roof failures. You have this uplift force from the inside pushing up and then up top pulling as well. So similar idea here. The next one is, let's say you have wind direction, but the cut or the opening is on the leeward side. You're now going to enhance, you're actually going to counteract the forces on the leeward side, and you'll pull down a bit more on your roof now, is what will end up happening with that force. So these are some of the nuances that go into just wind affecting our structures, and understanding that there's a difference between having an enclosed structure and then having one that's been punctured. And so why is that important? If we look at, say, an entire community, and so we've got a grid layout here of just a bunch of houses, and this is from another study I read, where they looked at, if you just have this wind field and you have these closely packed together houses, how do they impact each other? So what ends up happening is that this first house actually won't see as much damage, but the damage it does see generates debris, and that debris flows downfield into the rest of the houses and can puncture the other houses. So what you end up seeing is that this house right at this back corner actually has the most damage because it's also taken in all the debris from its neighbors. So this dense cluster of buildings has created a situation where you can have more debris in the air, which is what gives that puncture to the building, which is what makes those inward pressures so critical. All right. Another thing we had to consider in building this network was also that no location is the same. So if you're going to have a hurricane hit one of the examples I have up here is Manhattan versus, say, another example I have on here is Corpus Christi. Those are not the same location for a number of reasons, which are probably obvious to most of you on here. And you know what? Let me throw that out. What are some of the differences I would want to consider for a hurricane here?
Height above sea level?
Height above sea level, yep.
Presence of wetlands.
Yep, presence of wetlands. Density of buildings, yep, that's one too.
I guess to be more specific, actual like amount of vegetated surface in terms of the, I guess, sorry, submerged vegetated surface, I guess to be more specific on that.
Yep, definitely. Intensity of hurricane, yep, we're getting to the hazards there.
Latitude.
Latitude, okay. Let me ask this. What's going on here in Corpus Christi?
Development on a barrier island.
Yeah, development on there is bad. I was more so thinking like it has a barrier island. So all of those are just geographic considerations that we have to take into account when we're modeling those impacts. Because as soon as a hurricane hits, say, Manhattan and dumps a bunch of rain, it being so urbanized, it's not going to absorb it as well as some of these areas with wetlands that are used to having to absorb large amounts of water. And then places like Corpus Christi that have barrier islands, and much like the Outer Banks, which are barrier islands, they serve to kind of provide a buffer to the inland area from storm surge. Another part of this is how the hurricane tracks. And specifically, if I look at DC here, for the most part, DC is pretty protected. In order for a hurricane to really cause significant surge right in here and along the Potomac, it would have to track in such a way that the right-hand side tracks over this very sliver of inlet right here. It's pretty difficult to get it to be just exactly that position. So it's almost like it's got a little bit of protection for that city. But if it does, that's kind of an issue, if it does track that way. Similar to the case with Hurricane Sandy with New York, if you have the landfall south of Manhattan, which it did, it's going to start pushing in water into this bay here, and then push into New York, which also is got like, it's built up. It's got concrete seawall type things on the sides. If you've ever been to the city, it doesn't have a natural coastline. And then the same thing also considering for New Orleans, if you were to get the surge to go right into Lake Pontchartrain like that, that's more concerning. And again, with the barrier islands protecting Corpus Christi, frankly, if you're out on the barrier islands, I hope you accepted that risk. So those are also what we had to consider. All these things go into when we start to talk about impacts. So there's a lot of variables at play, including, the intensity of the hurricane. So the wind speed, the storm surge, the rainfall amount, all of that, but then how those differ by your location. And then also, as you differ those, how that impacts your infrastructure. Another thing to note is with those locations, their infrastructure is not the same. So for example, one of the things I'll note is that Manhattan, so New York, New Jersey, most of New England is going to be very old infrastructure. I'm talking like, I grew up in New Hampshire, I'm like 1800s old. Versus you go a little bit further south, Corpus Christi hopefully has more new stuff. We didn't have building codes until the 70s. So keeping that in mind, that's an aspect. And then our infrastructure, how dense it is. Manhattan's going to be more dense than down in some areas in Texas. Another part of that is again, with age is there are actually still in Boston brick culverts. So there are areas where you don't even have up-to-date stormwater systems, not even in capacity, just material-wise. So these locations have so much different about them as well. So we wanted to be able to consider that. Additionally, having said all that, how do we currently rank our hurricanes? We rank them by their wind speed. We go through the Saffir-Simpson wind scale and we rank it just by its intensity. The downside to this is that a lot of people tend to take that as a communication of risk, which it's not. It's a communication of wind speed, but it is not necessarily a communication of risk because that depends on other factors concerned with the hurricane as well as the location of that hurricane. All right, so that was hurricanes. So one of the reasons we don't yet have a ranking system like the Saffir-Simpson scale that also takes into account all those other hazards is because, one, it matters what place you're in, but the relationship between those hazards in that place to communicate, to get to impact is a very nonlinear. There's not something that's very direct to say this correlates with this intensity hurricane, which is going to correlate to this level of damage no matter what. So we explored some nonlinear ways to go about this. And one of them is using artificial neural networks. So let's talk a bit about what those are. So you've probably heard the name floating around a bit. It's grown in popularity since I started working with them. So there's this whole realm of artificial intelligence. Artificial intelligence encompasses everything from like just pattern recognition to things like consciousness in a machine. So it's all these things. Within artificial intelligence, you have machine learning. Machine learning is basically things that would be pattern recognition. It's teaching a machine to learn for specific tasks and for specific data. Where artificial neural networks fall in are as a type of machine learning. So you can also have, say, fuzzy logic for machine learning, something like that would also fall under that. But we decided to go with artificial neural networks. So, like I said, these are basically pattern recognition. What happens is it takes in all the information as, say, an expert in the field would, takes in all those different variables we just talked about, and treats them, finds the pattern between them to give you an outcome. So if you've ever noticed with oncoming hurricanes, those who are forecasting them, when they start to use the really strong wordage in the warnings, in the advisories, that's an expert speaking to you like, this is going to be bad. Don't listen to this one parameter. You want to consider this one as well. And so we were trying to get some sort of form that would help us synthesize that same type of process. And how we do that as humans is by learning through patterns. And so we're going to do the same thing here with machine learning. So artificial neural networks are set up in the very basic example, something like this. You've got input nodes with however many inputs you're going to have. Let's say, for example, storm surge, wind speed, precipitation, all of that. Those connect to hidden neurons. With deep learning, you can have multiple hidden layers. So hidden neurons are just serving as a connection from your inputs, and there's a certain number of those. You can change however many you want in the hidden layer. And those then each connect to an output neuron. So whatever you're trying to forecast or whatever you're trying to predict as an output. How this works mathematically, and I won't get too intense on this. If you like the math is there, but I'll try and generalize it. So how this ends up working is that you'll end up with variables. So for example, like 30 could be 30 inches of rain, 120 could be 120 miles per hour, 2,780 could be something like, I don't know, population. But I basically threw in all different scales of numbers here. you want your data going into the neural network to actually be on similar scales. So the first thing you do is go through these, you transform the data so that it has some sort of S shape between 1 and -1. You can also bound it by 1 and 0. It just depends on the problem you have at hand. For ours, we ended up with 1 and -1. So you first go through and get all of this data into this type of form. And then it's going to track through to our hidden layers. And again, track through to our output layers. Now, these connections between each of our layers have associated with it a weight between each connection. They also have associated with it a bias on each neuron. These weights and biases get adjusted the more you reiterate the data through the network. So you'll go through and have it go through a batch of the data. First, you'll get an error. It'll take that error. And there are various methods to do this where you try and minimize that error and relate it to the weights on the connections between the neurons. You then take that, you propagate that back through so that you can adjust all those weights. And then you run the data through another batch again and see if you've lowered that error. And you keep doing this over and over and over again. And when I say you, I mean the machine. You keep doing this until you reach that lowest mean square error, or lowest, there are like 3 ways to measure it. I typically use mean square error, but until you reach that lowest value. The models for the hurricane impact level ranking system use Bayes theory to adjust their weights going back. You can also do this with topics such as like gradient descent related to that, or a whole bunch of different other areas. We just did a bunch of analysis to find that the Bayesian method works best for our data. All right, so how do you generally go about, and again, very general, building a neural network? So the first thing you're going to have to do, you're going to need to gather data, and your data is going to have not only known inputs, but a known output. So if we're forecasting hurricanes, we not only need to know the hazards, so rain, surge, wind, the location of landfall, say the population affected, all of that. We also then need to know, what are we trying to forecast? So we say we want impact, but how do we communicate that? Are we talking damage dollars? Are we talking people dislocated? What have you? So once we decide that, we also have to find data that's available on that. So you can't just say you want it to predict population dislocation if you don't have past the events to give you all that data. And one of the tricky things is that we do a great job of recording all of our super extreme hurricanes. But then when it comes down to like our run-of-the-mill smaller events that kind of are like a blip, and people in North Carolina are like, man, whatever. We don't really record those. And so trying to find the data across the entire spectrum can be quite difficult. And so you need to be able to find it for those low intensity events and those really high intensity, high impactful events. So you want the whole spectrum so your pattern recognition is complete. Once you do have all of that, and I say that like that's little, I kid you not, of this graph, gathering data is like 90% of the work. Everything else after this is not as hard. You then take the data and you divide it into 3 segments, typically: a training segment, a validating segment, and a testing segment. And so you've sparsed out that data. So most of the data is going to go to training. And what that involves is being fed through the network in batches, where it's going to adjust those weights and biases within the network until it feels like until it feels like it met its lowest error. It's then going to take that additional chunk of data that you put off for validation and then run those through a number of iterations to make sure that you've actually reached that lowest error. And if it confirms it after, say, 6 run-throughs, and it confirms that that is in fact the lowest possible error you could get, it's going to produce a network. And then it's going to take your remaining data and we're going to test that. And it's basically going to say, how well does this network perform given that it's never seen this data before? So it's treating the test data like it's brand new data that it hasn't seen. and you're trying to see how well that network it produced worked out. So are those weights and biases really giving us what we want? All right, so they're data-driven, being the main takeaway there. In an ideal case, you have thousands of data points. I'll be honest with you, the hurricane model does not have thousands of data points because those data points also need to be consistent, and we didn't keep consistent records. Also, a lot of it is spatial, and we didn't really have shape files in this area until like 2008, it turns out. So that kind of starts to trickle down and like cut your data a bit. Ideally, yeah, large data sets, they're diverse, they're comprehensive, meaning they cover the whole span of what you're looking for. In an ideal world, I'd have 1,000 hurricanes that hit every single point along the coastline at various intensities. So like I have one specific spot in, say, Tampa, Florida, that got all the intensities I wanted, but that's not going to happen in reality. But that would be ideal for building these kinds of networks. Because of that, also, the selection of your variables is really important because the network is only going to be as good as the data it gives you. And I often tell people, you know, it's not, neural networks are not a solution to everything. They're only as good as the data you build it with, because I could have told the network that one of the variables was number of ice cream cones sold, and it still could have found a pattern. Doesn't mean it's right. But one of the things to consider. Okay, so let's talk about the model now. First things first, we just talked about all the types of things that go into a hurricane. So first of all, let me ask y'all, how do you think we discuss hurricanes after the fact? How do we classify them?
Dollars and damage.
Yep, that's the big one. What else do we talk about?
Yeah, like mortality.
Mortality. Oh.
Mm.
Anything else? Deaths and injuries. Yep.
I guess certain kinds of environmental devastation, depending on, I guess, botanically focused.
Yep. And then in the chat, displacement of people. Yep, that's another one we use. So these are how we discuss hurricanes after the fact. So population dislocation, damages, time required to recover is another one. You could also have the environmental ones. I tended to shift towards ones that were more people focused. We did momentarily debate deaths and injuries, but forecasting that seemed a little weird. So we kind of steered away from that. Also, because the goal of improving our warning system is to reduce deaths and injuries. So it was kind of counterproductive. You can't move a building, so that seemed like a good way to go. So we went with economic damage. You can easily find the total economic damage for a storm, all historic storms, because the National Hurricane Center puts out those reports at the end of each year. So we used those and went with economic damage. So then we have what variables contribute to damage. So there's all the hazard intensity ones, wind speed, storm surge, rainfall. We also determined that location for where it made landfall was important, a bit on its geography, a bit on the people that live there as well. The infrastructure that's located there as well is also important. And then the amount of people affected. So one of the things with Hurricane Sandy, and I say Hurricane Sandy because it was at one point a hurricane, what it was at landfall is up for debate. But it was huge. When I put its wind swath on a GIS map, it took up like the whole Northeast, like all of it. Just all of the Northeast covered by Sandy. So the size of it can affect the population affected as well. So then the other thing to consider, you have the inputs and how they relate to your outputs, but who's the end user of your model? So we wanted to be able to have something that would allow us to communicate intensity of a hurricane or apparent risk of an oncoming hurricane, so that it could be used hypothetically in conjunction with the Saffir-Simpson scale. So the ultimate goal is we were creating something for the public, which means we needed to have the model predict something the public could understand, which means everyone understands money. So we went with economic damage and we put it in systems we're all familiar with. We're familiar with the Saffir-Simpson scale being 0 to 5. We're familiar with the Fujita scale being 0 to 5. So we put it in a similar format where I divided everything up by common terms you hear is thrown about with hurricanes. One of them being the $1 billion hurricane. So if it is an impact level 3 or higher, it costs at least $1 billion in damage. This small one down here, I know 25 million doesn't seem like a lot, but in terms of infrastructure projects, I assure you it is low. But 25 million is basically the threshold for when the National Hurricane Center doesn't even report the amount of damages in their TCRs, their tropical cyclone reports. And then I wanted to make sure that whatever a 5 was rare. So in the data set to date, I think we only have 4 impact level 5 events. And that's Katrina, Sandy, Harvey. Actually, I think right now it's just those 3 because I think Irma is technically still a 4 by definition. I haven't adjusted the dollars to more recent than 2016 yet. But I think Irma is still right at the borderline. So it might just be those 3. But I wanted that to be a rare occurrence. You don't want to commonly say something is an impact level 5 and really just lose the meaning of something being catastrophic. All right, so how the model ends up looking is each one of these items is an input neuron. So the population affected, so that's everything that falls within the tropical storm force wind radii. The minimum pressure at landfall, the maximum wind speed at landfall, maximum storm surge at landfall, and the total precipitation over the event on landfall, because that's what we're interested in. And then you have the possibility of up to 4 landfall locations. And this was done intentionally because if you have ones that track up the East Coast, what ends up happening is, say, they'll landfall in North Carolina, they'll go back out, they'll be out at sea again, technically, and then maybe they landfall in New England. And there were quite a few like this. There was one really annoying one that I kid you not, like its path went, and it like looped in the Gulf and then went back to Florida. It was like, hey, here's Texas. Oh, no, wait, here's Florida. And so trying to communicate that was a little tricky. So we just put in that there's 4 possible landfall locations. 4 was the max we had in the data set. So like Katrina would have lat 1 and lat 2. So lat 1 and lon 1 as Miami, lat 2 and lon 2 as New Orleans, or Mississippi technically. All right, and then each of those connect to 1 through 10 of our hidden neurons. We ran this through with multiple iterations of how many hidden neurons. 10 ended up being what we went with. And then each of those hidden neurons connects to a impact level. And each impact level, so what the model ends up outputting is on a scale of 0 to 1. And that 0 to 1 gives you like a likelihood of how confident the model is that it would be one of these impact levels. I've since come up with rules to program for it to tell me which it is. Because once it gets to 4 and 5, it starts getting a little tricky in its confidence because it's like really hesitant to forecast a 5. But typically, if it's pretty confident, like say an impact level 2, everything will be close to 0, and then the impact level 2 will be close to 1. So that's kind of how our output reads. All right, I'll kind of quickly go through this. Evaluating a neural network, there's a few ways we do this. There's the performance during training. So this is how the error looks once it goes through all of its iterations, and then you'll see like a sharp drop off. and that's when it's reached its lowest error. So first we evaluate that it's actually reached a lowest error by this graph. Then we go into what are called receiver operating characteristics, which give you true positive and false positive rates. So it's like crying wolf versus being accurate. You want all of them to pretty much cluster right up here. So this is all the same model. And then you have a confusion matrix, which I always find funny because it is kind of confusing to look at whenever you look at it the first time. But essentially this diagonal is telling me that I had a target impact level that I wanted to place an event at, and the neural network placed it as that event along the diagonal. Now, if it misplaced an event, so 2008 Eduard, I think it's Eduardo, I think that's a typo. The impact level was supposed to be a 0, but it forecasted it as a 1. And so that's one variable that ended up being one data point that ended up being off. So all the way down the diagonal, you'll see you have its accuracy rate and its overall percent error. You don't want a 0 as your percent error because that just means the network overfit the data, and there's no such thing as a perfect model. So that's not going to happen. In real time, how we use this is each NHC advisory that's issued comes with data on the hazards. It also comes with a GIS file that allows us to take the wind swath in the forecasted wind swath and then try and grab the amount of population to be affected out of that. So we take those advisories, we gather that data, we then put it into the neural networks. And I don't just use one, I tend to use 11 in an ensemble, much like we do with hurricane forecasts. We have multiple models working at once. So I have, for the 2017 model is what this one's for, I have 11 neural networks working simultaneously with the same data, and then those are averaged to give me an idea of what is most likely to occur. So we ran this real time for Hurricane Harvey. So that was interesting. It started out kind of boring. We're like, oh, okay, I mean, it's another 0. That makes sense. It's fine. I then flew to Virginia Tech and was like helping my stepbrother move in. And so I was not worried about having to do this. And then the forecast got updated. Now we're looking at upwards of 64 centimeters of rain. Things started looking a bit more intense. And we jumped up to a forecast of impact level 2. Once we got up to close to what the actual rainfall was, jumped right up to an impact level 4. So you'll notice as time went on and our forecasts improved meteorologically, so did the forecast for our impact. And then this is what it actually was a 5. Again, it was just super hesitant to jump to it. What we found in doing this from 2015 to 2017 is that most of the forecasts end up converging around the 36-hour mark to its actual, what ends up happening. We do have a couple cases right here with Nate where it jumped a bit. So it forecasted and it got it a little later. But for the most part, it seems to converge around 36 hours is when everything is most accurate for us to forecast an impact. All right, I know this looks like kind of confusing, but basically another thing we did with it is we looked at if we held for each state, we took one location and we had a hypothetical hurricane occurring at that location. And we individually changed, say, the wind speed on its own while holding everything else constant. And then we changed the rain, held everything else constant, so on and so forth. How long would it take for us to go from a standard impact level 2 up to $1 billion event in impact level 3 to make that intense jump? One of the things we noted is that the hazards themselves, if we go, these were forecasted, we based those off of climate change models, although that might be different now. And then we looked at population growth projections and inflation. Most of these ended up, if you just count for inflation, that's going to happen by 2040. So by that standard, that's already going to happen. The next one is actually population increase is more vital to getting us into those billion-dollar events. Other thing we did was move them around landfall locations. I'm trying to make sure I have some time for questions. Moved them landfall locations. One of the things I'll note is that there was a tropical storm in 2013 down in Florida that was unremarkable. I moved it up to New York. It would have been remarkable. It would have probably been around an impact level 4 event versus if I moved Hurricane Sandy from New York down to Florida, where it would have dropped most likely an impact level. The other one I did was Hurricane Ike in Galveston versus North Carolina to compare an artificial seawall with kind of natural outer banks, so natural barrier islands. And we saw that North Carolina ended up with a lower impact level, but part of that was also the amount of population that was affected was actually significantly less than where Hurricane Ike hit. All right. So we're currently modifying it to be specific for North Carolina locationally to tell us where exactly you can expect the brunt of that impact to occur. This has been quite a challenge for me the past couple of years trying to get it to do this because the data is just such a pain. Like I said, 90% of the project. But we're trying to get it at least for the state where we can get a focused area of where all this impact is occurring. And my big cautionary tale whenever I give these types of presentations is just to mention that it's not a default way to model something. The reason that I think this works with this problem is because most of the people in this field already know that all of these things affect the overall impact of a hurricane. We just haven't had a way to mathematically correlate that. So it works for that case. But if you're not entirely sure what variables are going into your problem, then it's not recommended to use something like machine learning for that problem. And we need more research into what's actually causing that problem. All right, questions?
That's super interesting. So I worked back at my master's thesis, I used artificial neural networks for that work. And like a lot of these non-parametric solvers, they're sort of difficult to interpret why you got what you got. I mean, they'll give you a great answer, but why? And you make me think of that when you talk about Harvey, because Harvey and Houston were inland enough where I don't think tidal surge was a big deal, but they just got swamped by rainfall, right? Whereas usually a hurricane's got a lot of tidal surge problems. Mm-hmm. So, and it seems like it picked it up just fine. So, you know, if you have this, if you've got 36 hours out, you run it, you see it's going to be a bad storm, can you dig in and find out what's, you know, do you have to worry about rainfall, or do you have to worry about the wind, or do you have to worry about, you know, which of the parameters?
That's a very good question. Because I haven't specifically done it in that aspect. I've more so done hypothetical scenarios to make sure it's picking up on that. There's other work I've done that's done exactly what you're talking about and trying to break apart what on earth that neural network is doing, because it's like it creates magic connections. But to be honest, I have not applied that method with this specific neural network. I applied it with another one. But that would actually be an interesting question, because I've only done it ad hoc, not real time.
Mm-hmm, mm-hmm. Well, if you had that information, it might allow disaster professionals to prepare some. So thank you.
Yeah, of course.
Thanks for your presentation. Actually, recently we are working on modeling this different types of natural hazard, including hurricanes. So it's pretty helpful to understand this. So, so I have two questions. So the first question is, could you go back to the table? You define different impact levels.
Yep.
Mm-hmm. I think it's at pretty beginning. Oh yes. So, so you define different impact levels by the economy damage, right? Is that correct? Okay. So, why you use the impact level as the output instead of directly use the economic damage here?
Yeah. That's a great question. I did start out with trying to forecast the number for the economic damage.
Mm-hmm.
Couple things. The type of neural network I was using does classification. So it works better in a classification system, which is what the impact levels are. Okay. Another part of it being that I didn't want to forecast an exact dollar amount. What tends to happen communication-wise is if you tell people it's going to be $125 million, they're going to hold you to that number.
Oh, okay.
So putting it in a range was kind of my mischievous way of getting around the fact that everyone thinks a forecast is exact. And that's not usually how forecasts work. So I made it a bit more generalized.
Okay, well, thank you.
Yeah.
The other question is, could you go to your the neural network? I think it's the hurricane impact level model.
Oh, so the one with the variables in it?
Yes.
This guy?
Yeah. Yes. So do you mean you use so I mean how do you input your longitude and latitude data there?
So I put it in terms of degrees north and degrees west. I've only programmed this neural network for the United States. So I don't even consider positive or negative. I just do degrees north, degrees west.
Yeah, I mean, as you listed here, do you list it as variables like longitude 1, longitude 2?
Yes. Yeah. Okay. Yep. Mm-hmm. So the latitude alone is one input neuron. The longitude then is one input neuron. Latitude 2 is another input neuron. Longitude 2 is another input neuron. So I believe there's 13 input neurons total.
Okay, so what are longitude 1, 2, 3? What are these points? The trajectory of hurricane or something?
Yeah, they're meant to communicate trajectory and multiple landfall locations. So for example, if I just took where it first made landfall, I would have Katrina as hitting Miami and not New Orleans. So being able to communicate that it made landfall in Florida and New Orleans is the purpose of having these multiple landfall locations.
Okay. Yeah, my other question is, could you let me have a look? What does your training data look like? Because I was a little confused about this. Could you describe to me a little bit, what does your training data look like? So
for the inputs,
mm-hmm.
Okay, so the inputs, the training data, so it's population number mm-hmm. of people within the wind swath. We've got a number for the minimum pressure, mm-hmm. got a number for wind speed, a number mm-hmm. for storm surge, and a number for precipitation. Mm-hmm. We then also have a number corresponding to latitude in degrees north, and then mm-hmm. longitude in degrees west. Mm-hmm. And then if it's applicable, we have a latitude value for longitude for the second landfall and a longitude value for the second landfall as well. Mm-hmm. And it keeps going as applicable. If it's not applicable, technically the data reads as 0 in landfalls 2 through 4. Mm-hmm. And I know that sounds weird because technically that is a place on the map, but remember I trained it just for the United States. So 0, 0 is not a point within the United States.
Okay. All right, thank you.
Yeah.
Thank you.
Yeah, I had a quick question as well this time. Excuse me. Yeah, and excellent talk, by the way. It's just really fascinating work, and I think could have a lot of application to communicating hurricane risk. So my name is Jack. I'm an atmospheric scientist over in Geography and Earth Science. So I'm a colleague at Casey's. So I was just wondering, sort of more on the atmospheric side of things. So on this slide, the variables on the left in blue there, so the pressure, the wind speed, the storm surge, and so forth, are you just using sort of like NOAA's forecast of the minimum pressure at landfall there for pressure, or is it the entire pressure field, like in longitude, latitude, and time?
Yeah. So pressure, I'll also say pressure is one I debate whether or not I should even have it in there. Because when
I wasn't specifically asking about pressure, but more like just in general for those blue variables.
Oh yeah. So
is each of those one number?
It is one number.
Maximum or minimum at the landfall time, or is it the geographical field of whatever that quantity is that's being produced by like a more model? So it's just the one number.
It's just, so I just put in, say, the maximum storm surge.
Okay, and then like the
entire storm.
So this will be like the maximum forecast preset from the NOAA.
Yes.
Preset for that, and then the maximum wind speed and so forth.
Yes.
Okay.
What we're working on now is what you're talking about with the really gradated scale. It just involves overlapping wind fields as a GIS layer, and then overlapping it with buildings as a GIS layer and census tracts as a GIS layer. And so I can't tell you how messy this is right now. But, so getting it in that gradated scale is just a lot of overlapping. And that's currently what we're working on, is to get it more specific to like what you're talking about.
Oh, I got it. Okay, so that's the direction it's moving. So eventually you might like an entire forecast precipitation field from NOAA rather than a preset.
Right.
Okay, great.
Yep.
Yeah, this is already amazing though.
Thank you. And then I see Casey put a question in the chat. Smaller scale impacts. Tornadoes. I have momentarily considered the presence of tornadoes. My biggest concern is that it's not as forecastable as the other hazards. And since you're trying to use it real time, kind of throws a wrench into things. So as of right now, I've still left that out. And then the next question, producing geographic map of these impact levels. Yes. So that's along the same lines as what Jack was asking, is that, yeah, the idea is that, and we're starting it with just North Carolina, because we're starting it with one state, because not every state's going to be the same with data. So we're trying right now to get it so that it would be like when you see a precipitation map and it's color coded by intensity of precipitation. We're trying to get it to the point where you could actually have it go, the entire state of North Carolina could be color coded based on how much they're expecting impact wise. And we're doing it in terms of cost still. And so we're going to end up looking, right now it's at zip code level, which is also, if you've ever worked with zip code data, GIS isn't also a freaking pain in the butt. But you would have each zip code correlating to an expected amount of damage dollars.
Well, this has been a fantastic talk. And if you look at the chats, everybody really appreciates what you've taught us today. And it's an exciting horizon. It's great to see where this will go. So we're at the end of our hour. And so if we would like to give Stephanie a bunch of clappy emojis. Thank you so much for talking to us. We really appreciate it.
No problem. And I'm putting my email in the chat if you have any, if anyone has any further questions. I'll put that in there. So
well, great. In probably a day, I'll have this up on our YouTube channel. So anybody that wants to review it, or if you have a friend that didn't see it, or Stephanie, if you want to show it to a class and save a lecture, you can get it there. So thanks again.
Hi, thank you, everyone.
Bye-bye.
Thank you.
Thank you.